So this is a kind of a shoot for the stars and maybe you'll land in a tree kind of problem, where I don't know if you would be able to get all the parts, but there are certain parts of this that I definitely would want you to be able to calculate, especially based on what you know from calculus class. And other things maybe you won't be able to get, but that's okay. I'm going to actually work out this whole thing. So we have a box. It's being pulled according to this equation, and we want to know a couple of things. So first, we want to know the speed of the box at time equals 0. And when I'm looking at these different things here, and I've been given a function like this, I'll tell you my best idea is to take derivatives. So I know x is going to be 1/2 t cubed plus 2t. So my first derivative, that's what this little dot means, is going to end up being 3/2 t squared plus 2. And then my second derivative, which is the acceleration, is going to end up being 3t. Excellent. So the speed of the box at time equals 0. I'm just going to go ahead and get that. That's going to be 3/2 times 0 squared plus 2. So that's 2 meters per second. Now I want to know the kinetic energy of the box is a function of time. That is interesting. So to get that, that's going to end up being 1/2 times 100 times v squared. Well, we got v right here. That's what this derivative is. So I'm going to end up getting 50 times 3/2 t squared plus 2 quantity squared. I would leave it like that and actually not try to do anything else with it. Just leave it like that. Now it says, what's the net force acting on the box? So that's going to be, the net force is F equals ma. So that's going to end up being 100 times a, which is 3t. So that's 300t. Now there's two ways we can get the power delivered to the box. One is we could take the derivative of the work. The other one is that we can do power as force times velocity. And that's kind of suggested to me because I've got the speed, I've got v as my derivative, and I can times that by f. So if I were to get the power delivered to the box, I'm going to actually do part 3 up here, and that's going to end up being P is F times V, and that's going to be F, which is 300T, times V, which is going to be 3/2 t squared plus 2. That's how I would end up doing that. And then we want to get the net work done in the box in the interval 0 to 2. So the way I would do that is I would get work as the change in kinetic energy. And so I know the kinetic energy as a function of time is going to end up being 50 times 3/2 times t squared plus 2 quantity squared. So now to get the change in kinetic energy, that's going to end up being 50 3/2 times 4 plus 2 squared minus 50 times 3/2 times 0 plus 2 quantity squared. And when I actually end up calculating that out, well, I'll actually go ahead and get that number for you. And I'm getting 600 joules worth of energy there. So that's for part C. And it says the work done by the student on the box would actually need to be greater than, because this is the net work done. And it's a rough surface. So that means the total work done is the, if we draw a free body diagram, we got normal, we got weight, we've got the student, and we've got friction. So the student actually has to do work to overcome friction. So greater than, because student does work to overcome friction. I think that, let me just make absolutely sure, I think that pretty much wraps up the first problem. So that's the 2003 problem.